Hello everyone, this is Cameron Snow with Danomics.com. I am one of the co-founders of Danomics and I lead the subsurface development of the platform, and I am a geologist and petrophysicist by training. In this webinar, I'm going to be covering multi-well petrophysical analyses and some of the special techniques and approaches that we take when performing those. So with respect to what we'll cover in this webinar, we're going to start off with what are some of the differences between single well and multi-well petrophysics. Then we'll talk about some of the prerequisites that you need to take care of before you start your analysis. Then we're going to look at data prep and conditioning and the special role that it plays in these type of projects. And finally, we're going to wrap up with how you should go about setting parameters in these. So why is it that we do petrophysics? Well, we are looking to accurately describe the reservoir fluids and properties. So what's your clay volume, your porosity, your water saturation, etc. And often associated with this, we then want to flag intervals that are capable of flowing some type of fluid, whether or not it's oil, gas, or water. So these are our net pay and net reservoir flags. And ultimately, what we want to do is we want to provide an indication or predictor of reservoir performance. So, if we mark something as having good petrophysical characteristics, that should perform better than something that has poor reservoir characteristics. And if not, then we either need to understand why. Is it something outside of petrophysics, like completion design or lateral length or depletion? Or is this a sign that our model has gone awry? So, that's our ultimate goal is to try and be predictive with petrophysics. So we're going to spend a lot of time talking about single well versus multi-well petrophysics. What are the differences? Well, what I'll say is there are no real differences with respect to the methodologies that we're using. We're still using the same methods to calculate V clay or porosity or water saturation, et cetera. And a lot of our objectives are the same as well. We're going to go through and we're going to apply some type of workflow to quantify those reservoir properties and identify the reservoir fluids. And we do this with the idea that we want to generate some high quality work product that allows us to have an impact on the business decision and make the company a bit more profitable, hopefully. However, there are significant differences with respect to the execution between single well and multi-well petrophysics. So with multi-well petrophysics, all of a sudden we have to manage data from multiple sources and multiple generations. We have to not only worry about parameters within a single well, but now we have to manage those parameters across hundreds or thousands of wells even. And because we're no longer looking at a point in a system, we're now looking at an area or a volume. We need to make sure that we integrate regional knowledge and that we are consistent with that, with our spatial understanding of the system. And the idea is that when we're working across these multiple wells, that we're going to create a high quality enough work product that allows us to optimize these business decisions at a meaningful scale. And hopefully the small cumulative impact across the entire acreage base, is enough to meet or exceed that created, via a more detailed analysis on a single well. So when it comes to single well petrophysics, if we think about how that's traditionally done, it's this extremely detailed petrophysical interpretation where you go in, you spend a lot of time on data QC and repair, you manually establish parameters zone by zone, you're calibrated to your core and your fluid data. Depending on the well, you may have specialty data like NMR or MRI. And achieving this type of petrophysical sophistication is not an easy process, and this can often take multiple days. So the question is, what do you do when your geologists and engineers are asking for hundreds or even thousands of analyses? All too often, the answer that people go to is bulk log calculations. And this is where you identify a set of equations that you want to use. So for example, V clay from gamma ray, a density porosity, and a Archie saturation, for example. And then you apply those equations using often the same parameters, either in all the wells or in and sometimes even in every zone. You're not calibrating to any specific well, and the QC process consists of dropping problem wells until you have a map that looks smooth enough. And in my opinion, doing this leads to a very generic outcome. And if you're wanting to solve some more advanced problems, I would say the benefit of this approach is uncertain at best. Now, there is a spectrum between these two end members. Between our single well petrophysics, where we achieve, essentially petrophysical perfection, and our cookie cutter bulk log calculations. There's a whole spectrum in there. And where you want to be on this spectrum depends on the results, that you're looking to impact. Single well petrophysics, that is definitely where you should have things like, deep water Gulf of Mexico, pilot well on a pad. That's the realm of single well petrophysics. Bulk log calculations, if you're trying to decide if an area is worth a deeper investigation, bulk log calculations, can be quite useful with that. For a lot of the decisions that are in between those, that's the realm of multi-well petrophysics, whether or not you're doing infill drilling or reserves bookings or trying to help, use geology to influence, completion designs differences across a play. Those start to become the areas of multi-well petrophysics. So with multi-well petrophysics, we're trying to perform a detailed petrophysical interpretation, but we're trying to do this in a way that leverages automation so that we can interpret a large number of wells, and we're trying to use things like statistics and spatial data to inform our parameter selection. Hopefully we can still calibrate to core and fluid data if that's available to us. But instead of using some of these specialty logs, we're now going to focus on the more commonly available logs. And we do this because we want that impact to be broad. So a lot of doing multi-well petrophysics, it's about taking the time to develop this petrophysical blueprint, and then we can apply that blueprint to a large number of wells subsequently. So that's how we create that value. Okay, so with single well versus multi-well petrophysics, if we look at those side by side and look at the similarities, they are far more similar than they are disparate. Identify and apply a workflow, get the data ready to be interpreted, establish parameters, perform a QC, and then hopefully have that business impact that you're wanting to have. It's just that the scale that you're doing it on is different, and so at the end of the day, single well petrophysics, you're trying to make a targeted impact on the business, and with multi-well petrophysics, you are trying to have a smaller impact on each, across a large number of wells. So hopefully you have a large cumulative impact. But this isn't an either or type of decision. One of the reasons to do multi-well petrophysics is because that can satisfy a lot of your internal needs and create space so that the petrophysical staff can then apply their expertise on these very targeted value creation opportunities. So keep that in mind. Okay, so what are some of the prerequisites that you need to start a multi-well petrophysical project? Before you get started, there are kind of 5 things that you need to know. The first thing is you need a consistent stratigraphic framework. You need an appropriate level of subdivision. You need to have a top and a base defined of each zone, and without having this, it's going to be very difficult to get that apples to apples analysis across your area, and you'll end up spending a lot more time doing QC on the back end. So I would say definitely take the time up front to get this right. With respect to the data available to you, you need to know what data is available and what data is required. Do you need to have a full triple combo with a PE curve? Do you need a sonic tacked onto that, or can you do it with a more limited suite of curves? And how is that going to affect the variability between results? So you should think about that before you get started. You also need to think about how parameters change across the area that you're interpreting. So in this example map here, we have cumulative production from the Eagleford. We can see that GOR, is varying substantially as we move to the southeast. So we would want to capture that in our interpretation. We'd also want to make sure we understand, things like how does water salinity change, how does our temperature gradient change, how does source rock maturity change, etc. So we can incorporate all that into our analysis. So it's good to go through and build up a list of the petrophysical properties or parameters that we think will vary spatially. And then finally, we need to understand where to stop our analysis, and both in a physical sense and kind of a metaphysical sense. So in the physical sense, for example, as we're moving from somewhere like the Delaware Basin across the Central Basin platform into the Midland Basin, we are going, across vastly different geological provinces. So you need to segment your analysis smartly because you can't fit them all in one analysis. Like the changes in depositional system are just too substantial. So you need to make sure to split your analysis up and know where to put physical boundaries on it. In terms of knowing where to stop your analysis in terms of sophistication or techniques, what are you trying to use it for? Do you just need V-clay and total porosity and saturation, or do you start to need things like, synthetic shear logs, rock strength properties, effective stress, etc.? And understanding this could really affect how you decide to execute your workflow, what wells you use in your calculations, etc. So it's good to understand that beforehand. Okay, so once you know that, you're ready to move on. First step is to get your data ready to interpret. Log data has a lot of challenges with it. You've got issues with multiple curve mnemonics, multiple logging runs. There are differences in units. Is it percent? Is it decimal? Is it logged in sandstone units, limestone units, etc.? So we need to take care of all that. And those are what I call structural problems with the data. Then there's the second part of that, which is data that doesn't represent the subsurface. So do we have washouts that are affecting our data? Was the data poorly digitized? Are there variations in tool response, etc.? So there's handling that. And for this, I kind of view it as a two-track solution. The first track is handling the data attributes, so the structural issues, and the second part is handling data quality. So, I have an entire webinar, for data conditioning. So I'm not going to go into all the detail, but what I will say are a couple of things. First of all, you need to, do this type of work before you get into compositing your data together, normalizing it, doing the calculations, etc. So you need to have that alias table built out, and you probably need 5 to 10,000 curve mnemonics in it to be as thorough as you'd like. You need to have a workflow established for identifying the units, verifying the units, and making the conversion as needed for getting, things like density, porosity back into bulk density space, etc. And I suggest that you need to be as granular as possible in this. So, start very granular, and then you can combine things farther down the road. Because it's very hard to split things apart once they've been merged together in most cases. And I strongly believe that, every hour you spend doing this early on will probably save you 10 hours down the road of pain. So that's the data attribute side. Then there's the data quality side. And we're going to start off by looking at scale, which is normalization. So when do we normalize? Well, by all means normalize if you have variations caused by things like tool generation or differences between vendors. Normalize if it helps you with your correlation. And on the petrophysics side, if you have a sufficiently large data set and you can't go through and set parameters on a zone by zone, well by well basis, that's a good time to normalize. Now, what you shouldn't do is you shouldn't normalize when it results in losing geological information. So if you're normalizing away geology, that's generally not something you want to do. Also, normalization is not how you fix bad data. That is a separate step. And with respect to what to normalize, you can normalize any curve, obviously. Gamma ray is probably the curve that I see most commonly normalized, and it's also, just by its nature, one of the ones that's most amenable to normalization. What I'll say is just go through and be diligent to understand what normalization is doing to your data. Now, a couple of different ways you can do normalization. You can do a simple shift, and this is just where you try to shift the data to higher or lower values. You can scale the data, so this is a stretch and squeeze operation, or you can do a 3-point scale, and this is an asymmetrical type of stretch and squeeze. So you've got that combination, and then you can also do your scaling relative to either a fixed value or relative to another well. Fixed value is probably easier to understand. That would be saying like, hey, I want to scale all my gamma rays to be between 0 and 100. That's fixed value scaling. Let's scale all my neutrons to be between 0 and 40%. And then there's relative scaling, where you can say, hey, I want the, let's say the average of all my SP curves to align with each other, or I want to stretch and squeeze so that the P10 and P90 of my gamma ray in every well are aligned. So those are examples of relative versus fixed scaling. When it comes to doing this, the process that I like to take is I start off by making this property average map, zone by zone, log by log. I then determine if it needs to be normalized. I then select one of those methods. I apply it. I look at the magnitude of the change that has taken place, and then I look at the output. The goal here is not to have a perfectly smooth or flat map. The goal here is to make sure that your output more closely resembles the changes in the subsurface than your inputs had. So definitely take the time to QC this and understand the changes that have taken place. So once you've done that, then you probably want to focus on where do we have data that doesn't represent the subsurface. So, where have wellbore conditions resulted in unreliable log responses? Most often we do this for the density curve, so that's what I'm going to focus on. But we also need to understand what curves are reliable in washout zones, and then we need to decide what we're going to do to repair the curve once we've made those determinations. So essentially what we want to do is we want to take something like we have over here on the left, where we have this washout interval at the top of our log, and we want to repair it to something that makes more sense. Now, two-step process. First of all, we flag the bad hole. So we identify some criteria based on things like wellbore size, rugosity, the density correction, etc. We come up with a flag. We may need to pad that flag out. And then we need to repair the data in that flagged area. And this can either be done via things like simple correlations, or using machine learning like we do in Danomics, or interpolating data in from a 3D model. So a number of ways you can do this. But the objective in all the cases is the same, which is to start to get curves that are more representative of the actual subsurface than what we started with. And once we've done this, our data is now interpretation ready. So we got clear and consistent names, consistent units, consistent lithological references. Everything's been composited together. Then we performed normalization to make sure we have consistent data ranges, and we cleaned our data up by repairing the curves where we have washouts. And now we're ready to start our interpretation. And parameter evaluation and interpretation is a big part of the interpretation process. So when we think about how we normally set parameters, let's take, for example, our density porosity, for example. So we've got two parameters to set. we've got our matrix density and our fluid density, and we would go through in a single well analysis, and we would, at each zone, set this property. Now, the problem is this doesn't scale up well. You can set this on one well, no problem, but what if you have 10 wells or 100 wells, and this property needs to change from well to well? So there are techniques that we can use to address this. The first technique of which is parameter extrapolation. And this works great for properties that often come in from outside expertise or an outside data set. So here we have an example of maturity data. So if we were trying to calculate TOC, for example, and we're using the PASI method, which needs maturity, we've got this map that we've made, and we could say, okay, this well right here, we're going to extrapolate from the map this value, so we're going to extract that value and we're going to use it in this well. Now, I like using extrapolation from grids because it's useful for bringing in data from outside sets. We can make a sparse interpretation, to generate the map. The map inherently has QC built into it. I can look at this map and tell you, no matter where the well is, what that parameter value will be. So that is parameter extrapolation, and that's one way to spatially vary properties well by well, zone by zone. So we do this in Danomics. I would be happy to explain this to you in detail on a conference call separately, so just reach out to me and we can go over that. The next method is parameter interpolation. So imagine you have interpreted these wells that are represented by the blue dots here. If you believe that the properties vary in a consistent way between these interpretations, then you can triangulate a solution for wells that you have not interpreted. Now, of course, this assumes that the behavior between the points is predictable from our boundary conditions. If it's not, then this method isn't going to work, or we're going to have to be more granular in our interpretation. What I like about this method is with each new point that I interpret, my interpretation becomes more granular, more sophisticated. And it's also relatively easy to QC. We can generate a map from these points, and we can also just go in and kind of do blind checks to see if we're getting a good interpretation that's consistent with our thinking. These are what we call spatial tables in Danomics. Once again, if you'd like to learn more about how to use these in the platform, send me an email. We can set up a screen share to handle that. A third way to handle this is parameter remapping. And the workflow for this is you generate a bunch of statistics. You identify where on that statistical distribution that parameters have been picked, and that's what we call mapping the parameter to the distribution. And then we remap that to other wells. And so, for example, here in my Alston chalk, I identified the gamma ray clean as having a value of 16 in this well, and the gamma ray clay as being 195 in this well. And then in my target well, the remapping has told me, oh no, the value should be 14.8 and 190. And so, but you can see just visually looking at it that yes, even though those parameters are different, they are picked in the same style. And so that's what parameter remapping is all about. And then finally, you can look at something like conditional parameters. So you can set parameters via some conditional statement. So let's say, for example, we have a facies log like we see here. You could say something like, if it's limestone, then set our matrix density at 2.71. If it's sandstone, then 2.65. If it's dolomite, then 2.87, and so on and so on. Now this can work well, but what I will say is as the number of conditional statements increases, the more prescriptive it is, right? So, if you've got 3 or 4 lithologies, this could work great. If you've got a dozen lithologies, it can start to be very difficult to manage. Okay, so wrapping up, our multi-well interpretations, they are using the same methods and calculations and theories that we use in single wells. but we are going about our parameter selection in a different way. We're either extrapolating it from maps, or we're interpolating between values, or we're using remapping, or some type of conditional evaluation on parameters. So that way we can generate a custom interpretation for each well across a large area. And when it comes to QCing this, you need to QC not only the output petrophysical properties, but also the parameters as well. And I like to do this by evaluating things using zone-by-zone maps, because that's just a very easy way to see discontinuities and inconsistencies. So that is it for this webinar. I know we covered a lot, and I didn't go into exactly how to apply this in the software. I am happy to cover that with you. Just send me an email to csnow@danomics.com, and we'll get something scheduled. Thank you.